all you Business Cal students. Today we're going to go over the second part, or the second lesson at least, of the derivative, handout 4. And let's go ahead and take a look at this. So we want to recall the following. A tangent line, the slope of a tangent line, represents the rate of change of a function at a point. Right, that's what the slope of a tangent line does. And so it tells us how the function is, the slope of that tangent line tells us how the function is changing at that point. Okay? Secant lines approximate the tangent line when the 2 points of intersection are close together. So in handout 1, we developed a formula for the slope of a secant line. And this was it right there. Okay, and I know it says handout 1 here, but that was, if you recall, at the bottom of handout 3. So let's go ahead and fix that right there. So in handout 3, it's where we came up with this formula right there, and you recall this picture right here as well. And so I want you to take a second look at this guy here, and I want you to realize that this is also an average rate of change. Right? That's one way to look at that, right? Where the tangent line tells us what the rate of change is at an instant, secant line that tells us what the average rate of change is in between those 2 points, namely this point here and this point here. And so, there's a very strong connection between the average rate of change and the current rate of change. We use the average rate of change to approximate what the rate of change is at a given point. And knowing what the rate of change is very important, because you want to know if the investment that you're looking at, is that going to be increasing in value or decreasing in value, and so forth. So many applications to this. I'm sure you guys can think of plenty. And so note that if we were to bring the second point closer to A, so that'd be this point, we're saying if we bring this point closer to A, we are approaching a tangent line, because then this point would be coming in closer and closer like that. That's when the secant line starts to approximate the tangent line. And so we're actually going to apply a limit, right? We know we've been talking a lot about limits, and this is why we talk a lot about limits. We're going to take the limit as h approaches 0. Right? When h approaches 0, this distance right here becomes very small. And so we call this the instantaneous rate of change, or simply the derivative. And so we've got the definition of the derivative right here. A function f has a derivative at a if it is continuous. This is a very important part. If the function is not continuous, then you can't have a derivative there at a, which is defined as the derivative of a equals the slope of the line at a, right? That's the geometric definition. And this is kind of just a little bit of verbiage or nomenclature that's nice, short, and succinct, so that we know what's going on. Let's go ahead and zoom in so I can explain this. Here's our delta x, right? Delta y, or delta x, right? That's our change in y over change in x. That's what that means. And notice what's happening with the change in x. It's getting smaller. And we're saying, well, where are we interested in this? We're interested in when x equals a. Anytime you see a line that looks like this, that means such that. That's what that means. Okay, I'll go ahead and leave that note up there in case you want to go back to it. And note that we can write this, like this. And so what does this equal, or what can this be thought of? Well, that's our delta y. How can we think of this h? H is our delta x. Right, and so we're letting this shrink. So that's kind of what's going on here. So let's first look at this geometrically, and then we're going to go ahead and look at it algebraically after that. You know, look at it geometrically because we want to have a picture in our heads of what's going on here. So let's come over here. Note on this point, we've got this curve going on right here, right? That's our curve. And what is this line right here? What would you call this line right there? That's a tangent line. Right? That is our tangent line. So we want to know what is the equation of the tangent line of y equals f of x, right? You can see it's a tangent line because it's traveling, you know, in that manner right there on our curve. So the equation of the tangent line is simply this right there. We just read it right off the graph. Y equals x plus 1. And we want to know what is it going on at 0, right? So we're going to put our line there such that x equals 0. And so what is the slope of the tangent line there? It's 1, right? 0 plus 1. And there we go, that's it. And so let's go ahead and, slope of the tangent line, in this case, is that guy right there. Alright, so what is the derivative of f of x at x equals 0? That is, what is f prime at 0? Well, f prime at 0 is what we just found out before. It's 1. Okay, not too bad. So this should make sense to you. So if you see, and there are a few homework questions like this, so just make sure that you understand that the slope of a tangent line is the derivative of the function. Alright, so let's move forward. We're going to look at this algebraically now. Find the derivative of the following functions when a is 2, right? That is when x takes on the value of 2. And I want us to think about something real fast. Like I want us to really kind of think about what is the shape of these graphs. So this one, we've got our graph there, and it goes through like this, right? What's the slope of this line? Well, it's 1, right? Via y equals mx plus b. The slope is clearly 1 at the y-intercept of 0, right? Just by looking at that guy right there, we know this. So likewise, we know that the slope of any tangent line anywhere on this curve is going to have to be 1. Right? So we know that before we begin anything. But we want to get practice using this formula up here. So we know that if we don't get 1, something went wrong. So I would encourage you to try and work this on your own if you can. If not, that's okay. We're going to work it through together. Just kind of see how far you get. So go ahead, pause, try working on it, and then if you get stuck, no problem, just hit the resume button and see where I go with it. Alright, so the first thing we want to do is get our formula going, right? Again, we're using this formula up here. And so we're going to have f prime at 2, right, because we're using this value here. F prime of 2 equals the limit as h goes to 0 of f of 2 plus h minus f of 2 all divided by h. And so the next thing we want to know, okay, well, what is this guy? And so we need to evaluate, okay, what is this guy? So let's do a little side work over here. I'll do it in blue so you know it's side work. F of 2 plus h, right? And we're plugging it into this guy here. Well, that's just simply 2 plus h, right? Whatever shows up here, you put right there. And so that's what we have here in yellow, right? And now for the green. F of 2 equals simply 2. And there's our green. Right, again, whatever you put here, you place it there, right? Everywhere you see an X, you replace it with whatever you see there. Alright, let's go ahead and plug this in. We still have the limit as h approaches 0. And so we're going to plug this up on the top. 2 plus h minus 2, all divided by h. Go ahead and color code this so you make sure you can follow it nice and easy. And so let's go ahead and work this. Note we've got a 2 minus 2, right? So those are going to go away. So we're left with the limit as h approaches 0 of h divided by h. And so note what happens if you plug that directly in. You will get 0 divided by 0. This doesn't exist. You cannot do this. So we're not going to take the limit just yet. We're going to keep evaluating. We note that, this h will cancel with this h, right? So just leaving a 1 in both cases. So basically we're left with the limit as h approaches 0 of 1, right? And so we're taking the limit of a constant, and the limit of a constant is just the constant itself, 1. And so note that it corresponds with the limit, with what we thought it was going to be beforehand. Alright, so let's look at this next one, right? The other one was a little bit more clear than this one, because it's, straight lines, pretty obvious. But, this is y equals x squared, right? This is going to result in a parabola. A parabola looks right here, looks like this. And so I want us to think about, okay, what would a secant line at x equal 2 look like? 2 is, somewhere over here. Right, we'll draw that as a secant line. Note that the slope is positive, right? So we expect at least a positive slope. It may not be 1. It very easily could be another number. But we know that if we get either 0 or a negative number, something has gone wrong. Because we definitely can see that the slope of that tangent line is definitely greater than 0. So let's go ahead and work through this one. So again, we're going to find f prime at 2. And we have the limit as h approaches 0. And this is going to be f of 2 plus h minus f of 2, all divided by h. And let's do a little scratch work to figure out what these two guys are. F of 2 plus h equals 2 plus h squared, right? Again, just everywhere we see cx, we replace it with this term right here. All right, so let's go ahead and expand that term out. And so we're going to have 2 squared, and I know it's 4, but we're just going to keep it as 2 squared for right now, plus 4h plus h squared, right? And where if you're having trouble seeing that, this is just 2 plus h squared. What does that mean? That's 2 plus h times 2 plus h. And then you've got to just FOIL everything through, 2 to the 2, and then the h goes to both of them. And so when you do that, the first guy, you get 2 squared plus 2h, right? That handles this one and then this one. And now we're going to do this guy. Well, that's going to be plus 2h, and then finally the last one, plus h squared, right? 2h plus 2h is 4h, and that's where that 4h came from, in case you're having trouble seeing it. All right, so that's one of our terms, right? This guy, the one that's going here. Now that's just like that right there. And then the other term, f of 2, well, that's just 2 squared. Well, don't have to rewrite that, but we'll go and do it anyways. 2 squared. All right, so that's the next term. There we go. Alright, so we'll plug everything in. The limit as h goes to 0. And we have 2 squared plus 4h plus h squared. That's our first term. And then the next term, minus 2 squared. There we are. Now note, we got a 2 squared minus 2 squared. So those cancel. And so now we are going to go ahead and rewrite this without those terms. This becomes the limit as h approaches 0. Note that I'm writing the limit every time until I actually take the limit. And here we've got 4h divided by h plus h squared divided by h, right? All I did was just, I took this h and I distributed it to both of those terms. Or should I say that 1 over h. And so note what we have going on here. That h cancels with that h, and this h cancels with that exponent. And so we're left with the limit as h approaches 0 of 4. And the limit of a constant is just the constant itself. And so our answer is 4. This is a positive upward going slope. And if we go back to the drawing we had here, note that it is a pretty high slope. That is when compared to the slope from over here. All right. So let's go ahead and move on. Before we move on, actually, I want you to kind of look at this drawing that we had here. You note that we have this slope here where it was positive. But now if we picked a tangent line over here, anywhere along there, the slope would have been negative. And the further away from 0 you go, the higher the magnitude of your slope is going to be. So I want us to kind of be thinking through these scenarios as we go through both the problems in this handout and just things in general. It's a good practice to be in. Alright, so let's go ahead and look at this. If an amount of something can be expressed as a function of some variable, then the derivative of that function may be thought of as an instant rate of change. Right, and so, it's might seem like a bit of a misnomer since, rate of change is a measure of how things are changing. An instant implies no time went by, but it's the instant that's going by is just that, an instant. It's so small of a point in time. We just go ahead and say it's the instantaneous rate of change. All right, so let's go ahead and take a look at this. Right, here's a formal definition for the instantaneous velocity. And so note, it's got a very similar definition to the just regular derivative. It's simply the change in position divided by some infinitesimal change in time. An infinitesimal is just an incredibly small amount. Okay, and so we come over here. We note that we've got a very similar definition. I should probably put such that t equals a is the only thing really missing from that definition. Please draw that in on your own handout. But it leads to this final expression right here, which is identical to what we've been working through before. All right, so again, in case the geometric picture still hasn't cemented in your brain, we're going to go ahead and take a look at this definition right here. And so note, here we have, time is down here in the x-axis, same as over here. On this axis, right here, we're measuring distance, and on this axis here, we're measuring velocity, as in meters per second. And so we want to know what's going on with each of these. And so let's go ahead and take a look. What is the rate of change going to be right here? It's a straight line, right? So we can just kind of look at the slope and we'll be okay. So run over 2, run up 2. Well, that's going to be a ratio of 1 to 1. Rise over 1, the slope is 1. All right, since the slope is 1 here, we're going to go ahead and draw that in right there. That's how that works, right? So we draw our straight line into here, and we're going to go and put open circles on both sides. And the reason we have open circles there is because what's the rate of change here, right? We think of the rate of change as the slope of the tangent line. But what is the tangent line at this point right here? You could say that the tangent line goes like this, because it does go, it is tangent, it does go through that point right there. Or you could say that this is the tangent line, because it does go in the same direction, and it does pass through this point right here. It's ambiguous. It could be one or it could be the other. There is no predictive quality at that point. So we say that the velocity function does not exist at that point, and that's why we have that open circle here. And the reason there's an open circle right here is because we don't know what was happening just prior to. So we say we know what's happening immediately after 0 seconds, but we don't know what was happening at 0 seconds or right before it. So that's why we have the open circles. Alright, so right here you can see that the slope is clearly 0. It's a horizontal line. Slope's always going to be 0. So we go ahead and graph that in like so. And that goes on from 2 to 3 seconds. Oh, sorry, I should have continued that on for one more second. Make sure you fix that on your handout. Sorry about that. Alright, so from 2 to 3 seconds, it goes nowhere. So you can see, from here, from 0 to 2 seconds, it advanced up 2 meters, and then from 2 to 3 seconds, our object just stood still. It didn't move anywhere. And since it didn't move anywhere, that's why it's got a velocity of 0. All right, so now we note that, our object moved 2 meters away for the first 2 seconds, and now from 3 to 4 seconds, we can see that the object is moving 1 meter back towards us, right? So this is a drop down 1, and it ran over 1, so it's got a ratio of -1. So that means the velocity was negative, and so we go open circle here, and that went from 3 to 4 seconds. That's how that goes. And now look over here, from 4 to 5 seconds, the object moved away from us again. And how far did it move away from us? It moved away from us 3 meters. Right? It moved away 3 meters, and it took it 1 second to do that. So rise over run, 3 divided by 1, so that's a slope of 3. And so we come over here, and so from 4 to 5, we got open circle, open circle. And in case you're wondering, if you do not have those open circles, your graph is not accurate, right? You got to have those open circles to accurately depict what we know. So note what we've come up with over here. We now know just by looking at this graph, we can look at any particular second, and we know what the velocity of the function was, excluding the open circles, of course. And so this is a perfect intro to the derivative as a function. So while prior to we were looking at what was the velocity or the rate of change at a specific point, now we want to know what's going on at any point, right? We want a function that tells us that right off the bat, so we don't have to do that analysis for every single point. All right, so we say that a function f has a derivative at x if f is continuous for each x on its domain. And note over here, it's anywhere up here, any point that the original function was not smooth, we didn't have a derivative. So we want to add that to there. And so put and the function was smooth. That is, it didn't have any sharp corners. If the function is continuous and it is smooth, then we're going to have a function. All right, so we've got the slope of the tangent line at any point x, right? That's what this means, geometrically speaking. And so again, note that we've got this statement here. We no longer have the such that symbol because now it's for anything on its domain. If you wanted to put a such that, you could say such that you're on the domain of the function, but I don't think that's really necessary. And so we end up with this guy here. Go ahead and put an X over that because that should be X, not an A. And so note how very similar this function is. This statement is. The only difference is instead of a specific number A, now we have the variable X. So we're going to go ahead and find the derivative for the following functions. And we're going to use our knowledge of the derivative of this formula here to help us through this. Alright, so let's look at this one, right? We want to figure out what is the derivative here. Note this is a constant. If you were to graph this function, so those are x and y, if you were to graph that, that would have a graph that looks like that, straight horizontal, which always has a slope of 0. So we know that we're expecting this to have a slope of 0. If we get anything else, we messed up. So let's go ahead and work through this one. So f prime at x equals the limit as h approaches 0, f of x plus h minus f of x, all divided by h. Okay, so let's go ahead and work this through. First off, what is f of x plus h? Well, it's going to be 5, right? And you might be wondering, why is that so? Well, that x plus h, anywhere we see an x expressed over here, we replace that with x plus h. I see no x's over here, so there is nothing to replace. It will always be 5, no matter what value for x you put in. Alright, so what is f of x? Well, that is also 5, because it doesn't matter what x equals. The output will always be 5. That's the definition of a constant function. So, what is this guy here? Well, that's this guy here. What is this guy here? That's this guy here. Okay, nice and tidy. So this simply becomes the limit as h approaches 0 of 5 minus 5, all divided by h. Alright, so what's 5 minus 5? 5 minus 5 is 0. So again, we have the limit as h goes to 0 of 0 divided by h. Now we haven't taken the limit as h approaches 0, so we can still work however we want. So this is still 0 divided by some number. So this is going to become the limit as h approaches 0 of 0. Right? 0 is a constant. So the limit as h goes to 0 of 0 is just 0. Right? The limit of a constant is just a constant. And that is exactly what we were expecting. Okay, good. B, f of x equals x, right? The slope of this will always be 1. We know this from mx plus b. Right? So what's the slope? Right there, you clearly see no number. It's 1. It's going to be 1. So if we get anything besides 1, we've made a mistake. So having said that, let's go ahead and work through this. Actually, if you didn't do it for the A, I want you to do that for this one. I want you to pause the button. I want you to hit the pause button, sorry. I want you to hit the pause button and try and work this guy out on your own and see if you can get all the way through it. If you can't, don't worry about it. Just resume and just kind of go through it until you get a better idea. Alright, so f prime of x, that is the derivative, is the limit as h approaches 0 of f of x plus h minus f of x all over h. You should write this down every single time that you're doing this, so that way this starts to become second nature to you. Okay? So what does this equal? This equals the limit as h goes to 0 of x plus h minus x all over h. So I'm not going to, I feel like I've kind of talked about this one enough, so I'm not going to do the side work for you, but I am going to highlight so you can more clearly see what's going on. Okay. All right, so you can see we've got an x minus an x. And so we're left with the limit as h approaches 0 of h divided by h. Right? H divided by h, that's 1. So we're taking the limit as h goes to 0 of 1, and the limit of a constant is just the constant itself. Doesn't matter what the limit is. Alright, so that's that one. It doesn't matter where you are, the rate of change will always be 1 for every unit of x you advance to the right. Alright, now let's look at this one. 2x. I want you to think about mx plus b. And I want you to think about, okay, what should m be? It's 2, right? So the slope will always be 2. Right? That is the slope. Always. That is always the slope of the tangent line, because all tangent lines for a straight line are the line itself. So let's go ahead and work through this one. We have f prime at x equals the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Press the pause button now if you haven't done already, and try and work this through. All right, equals the limit as h approaches 0 of 2 times x plus h minus 2x all over h. Okay, and we'll go ahead and color code these so you can kind of see where everything is coming from. Good. All right, so let's go ahead and expand this term right here. So we have the limit as h approaches 0 of 2x plus 2h minus 2x all over h. So everything's been nice and expanded. You know, this term is still over here all by itself intact, and the same with over here. But note that we've got a positive 2x and a negative 2x, right? They cancel out, and so what are we left with? We are left with just the 2h on the top. And note that the h's cancel each other out. All we're left with is a 2. And that, of course, is going to be just 2. The limit of a constant is the constant itself. And note that is precisely what we were anticipating. All right. So now it's a little bit different. Now we got a plus 1. Right, we got a constant in the mix. I wonder if that constant value is going to change what our slope is. Is it going to change the rate of change, right? So we got mx plus b. Well, wait, the slope is just 2. The slope is still always 2. So our prediction is that the presence of this guy right here is going to have no effect when we run the numbers, right? It will always be 2. Does not matter if we bump the equation up 1 or any other number. So let's go ahead and work this through. F prime at x equals the limit as h goes to 0. F of x plus h minus f of x all over h. Hit the pause button, try and work through this one, and then resume. Limit as h goes to 0. Okay, so we've got 2, we got an x plus h, and we have a plus 1, right? That is our first term right there. And then we got a second one. We've got a minus. Let's go ahead and put parentheses up. 2x plus 1, because we want to make sure we distribute this negative over. That's why we have the parentheses. And note that, you know, this term is the same as this term here. Okay, cool. Let's go ahead and distribute this 2. And so we're going to end up with the limit as h approaches 0 of 2x plus 2h plus 1 minus, now I'm going to go ahead and distribute this negative sign to each, so I've got minus 2x minus 1, all divided by h. Again, all I did was I just took this negative and I distributed it to both terms. All right, we've got 2x minus 2x, and note we also have a positive 1 minus 1. So everything got wiped out. All we're left with is the limit as h approaches 0 of 2h divided by h. We note the h is canceled. And so we're left with the limit as h approaches 0 of 2, which, as we've already discussed, is 2. Exactly what we would expect. So now let's go super general on this, right? Let's go ahead and take a look at mx plus b. Right? You know, that's our, we're expecting that the derivative is going to be m, right? Because that's the rate of change. That's the slope. So let's go ahead and work through this and see if that's what we get. So we have f prime of x is the limit as h approaches 0 of f of x plus h minus f of x. So far, everything is the same. Nice. Hit the pause button, work through this one. All right, so the limit as h goes to 0 of m times x plus h plus b minus mx plus b. And let's go ahead and put the parentheses up because we do need to distribute that negative sign just like we did before. Alright, and so we're going to distribute the m and distribute that negative sign, so we have the limit as h goes to 0 of mx plus mh plus h, and then minus mx minus b, right? We distributed that m to both guys, and then we distributed that negative sign to both of those. All divided by h. Alright, let's look at what cancels. We got mx minus mx. Those go away. And then we've got and we got a b there. I'm going to go ahead and fix that up. Does not look, there we go. Okay, sorry, that should have been a b. I drew that funny. And we got a b minus a b. And so here we have the limit as h goes to 0 of mh divided by h. Of course, the h is canceled. And note that that m is a constant in this case, right? This m and b are both constants. X is the only variable. So the limit as h approaches 0 of the constant m is just going to be that constant. It's m. That's what we were expecting. Perfect. All right. Let's go ahead and take a look at this guy, number f. This, before we were looking at strictly linear equations. Those were easy enough. Now we're going to take it a step a little bit harder, and we're going to look at x squared. So f prime at x, again, that's going to be the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. So this one's going to be a little bit harder, but I still want you to press the pause button and try and work it out on your own. forget to write your limit there. And so we have x plus h, quantity squared, minus x squared. And so again, let's go ahead and highlight these so you can see what's going on. Good. Alright, so now we got to expand this term here. Alright, so all I did was expand the term. That's all I did. Note that this term is still equivalent to everything else you see in yellow. Then we have that green there. Alright, and so we also have an x squared minus an x squared. Those are going away. And so what do we have left? We have the limit as h goes to 0 of 2 times x times h plus h squared divided by h. So let's go ahead and distribute that h to both terms. So now we've got the limit as h goes to 0 of 2xh divided by h plus h squared divided by h. So here the h's cancel on that one, and here the h makes that square go away. Because keep in mind that that 2 right there means that there's 2 h's up there. And so what are we left with? We are left with the limit as h goes to 0 of 2 times x. Now I want you to note, x is a variable, but x really does not care what h is doing. So this simply is going to become 2 times x. And that is our derivative. So basically what's going on here is that depending on where you are in the curve, that's going to change the slope. So let's take a look at this in Desmos real fast. Alright, so here I want you to note that the g of x term is the derivative, and that the original curve is f of x, and that's going to be in blue. Why don't we go ahead and change our derivative? We'll try and keep that in red. I'll try and be consistent with that from now on. But we have this red curve here that's the derivative function, and this blue curve is the original function. And so note what's going on. When you're at 0, you know, if I were to draw a tangent line right there, what would the tangent line look like? Well, it would have a slope of 0, which is exactly what this derivative function is telling us. Note that for any function, for any value of x greater than 0, the function is always increasing. Note that the further away you are from 0, the more this function increases. And so likewise, the further away you are from 0, the higher the value of your derivative. Right? That is the value of the slope of the tangent. Note as you go to the left, you're always decreasing, right? You're coming down the slope, you're falling, and what's the derivative function doing? It's negative. As a matter of fact, the further out you are over here, the more negative it is. And so that's a little bit of the connection between these two guys. Alright, so let's go ahead and further this with just kind of by looking at what's going on with the tangent line. So let's go ahead and activate this line that I have drawn out here. I want you to note this is simply the form of y equals mx plus b. What I've highlighted there, that's always going to be the slope. And this right here will always be the y-intercept. That's how we have this set up. Let's go ahead and take a look at what goes on as we vary a along, and you can see that our curve is in fact staying even with, our tangent line is always even with our blue curve here. And what is the slope? The slope will always match what's going on down here. And so again, when you're over on the left, it's sloping down. And then as you come over to the right, it begins to slope up. Okay. Alright, so that's basically all I had for today. Go ahead and start the relevant homework and email me if you have any questions.